Welcome back to part 3. You recall that there were these lattice sections that we just wanted to ignore so far, but now it is important to analyze them one by one. Firstly, the initial part we must understand is there is an input. So we set a angular velocity initially for the telescope. Now this set is placed into the summing junction with a subtraction of the measurement transducer. And you recall that our measurement transducer is just H. Okay. For example, the measurement transducer was given as H equals 1, but for now we'll just consider it as a H. Now, this is moved into a proportional control, controlled using a proportional control law with a gain Kp. That's very important to understand, guys. That gain Kp is the controller that is adjusted such that your system contains stability or instability, however you like. And this has resulted into the system's dynamics. So what was our system dynamics? It's basically, read the question quickly. So, yep, angular velocity, this, that. So to achieve this is used for the whole telescope to be, okay, so it is usual for the whole telescope to be driven by a motor. So the motor is the system's dynamics. And what is the motor represented as here? Km. The motor's transfer function. So Km. How is the system moving? This is what you put here in this part. Okay, after the controller. Now, once we have movement in our system, we must then continue. What other variables must we consider that is affecting this dynamics of the system? So the other variable we must consider is its reduction ratio gearbox, as stated in the question. Via a reduction ratio gearbox. So therefore N, it was given as N. And you think we're done. That's it. But however, when we read the question further on, it says that there is an imbalance that the contact by operators and the mounting of the additional accessories can each apply a disturbance torque about the rotational axis. So therefore, this is where it gets tricky now. We must consider that there is a disturbance in the system, but where to add this disturbance? This is the dynamics, overall dynamics of the system. Well, this is actually the overall dynamics of the system. Now, in order for this physical dynamics of the system to have the disturbance considered as an important variable overall, we must sum it up again. There must be another summing block past all these terms that adds in or includes the disturbance. So a disturbance must be included. A second summing junction must be placed with another plus or another addition. And this disturbance we'll just call, for our case, TD, as given in the question. And finally, we have output. Now the output, like I said, is the telescope's motion with respect to what we have given it. So the telescope's transfer function, remember, telescope's transfer function, what was it, guys? 1 over, throw this term there, 1 over the inertia about the polar axis of rotation of the Earth plus its dampening coefficient, and you have output. Now, obviously there must be a measurement transducer in order to measure what is occurring, and this measurement transducer then checks whether the system has any errors or any offsets or whatnot, and this offset is then corrected via the summing junction over here. That's just some fundamental theorem about block diagrams. I'm just going to pause the video here, guys, one moment. And a block diagram is constructed and finalized once you consider every single variable, an output with regards to an input, the error signal E, we'll just call it with respect to S. This is with regards to the Laplace transform. And then you have your variables considered here. So this is your basic block diagram. Sorry about the messy look of it. Just I'm using paint with a mouse. And moving on, the next question asks us to determine the closed loop transfer function of the disturbance and the actual input without the disturbance. So firstly, let's find the basic transfer function of what it would be without the disturbance included, this entire summing junction here. What happens if this is neglected, the disturbance is neglected, and you just only consider the input with respect to the output? Let's just quickly do that. So whenever you ask for that, to neglect the disturbance, you state TD equals 0, and therefore your actual block diagram would look something like this. One second. Your actual block diagram would look something along like this, along the lines of this. Error signal, your gain, system dynamics, your actual system transfer function. You notice how that block diagram, you notice how that summing junction has been neglected now, and your output, and finally that moves into 1, which is your measurement transducer, which was being stated in the question that it is 1 for our case. And you notice that it just looks like the same, it looks something similar to the previous general block diagram configuration. So let's use our basic formulas from before. You get your output over your input, which results in your closed loop transfer function. Do you remember that? Your closed loop transfer function, which would then equal. Now let's start summing and multiplying everything together now. You'd first get Kp, your forward path, Kp multiplied by Km, this is your forward path, don't forget, multiplied by N, multiplied by your telescope transfer function, 1, divided by the denominator of your telescope transfer function, the whole thing divided by 1 plus the product of your entire complete loop. Okay? So this is similar to the term we have above, but this time you consider the 1 again. So we have another 1 here. The reason I put that down is just to show you how the measurement transducer is being included in the feedback loop. Basic math, just simplifying. I'm just going to skip this step, sorry guys. Okay, so once we simplify all these steps down, we simplify this transfer function here, the closed loop transfer function without the disturbance included. Once we just simplify it via simple mathematics, you get the result as the final closed loop transfer function neglecting the disturbance as this. Now, what happens when we do include the disturbance and we neglect the input this time? It gets a bit more tricky because you have to use a theorem of, not theorem, but a principle of working through actual block diagrams via the summing junctions. What do I mean by that? So first of all, you have your W in, your set angular velocity to a summing junction of plus. Now remember, I did say neglect your input. That's what you were asked for, to just consider your disturbance now. This is the disturbance section. But what's funny about that is we still actually do draw up a block diagram with your input. However, your input is actually going to be set to 0 this time. You're in. It's your summing junction with your disturbance. I'm showing you guys these steps because I just want to run through what's going on. So you notice that these